Hi everyone, welcome to this video. So now we continue to the last subtopic of chapter 5, which is 5.5, the mutual inductance. If we recall, previously we learned about self-inductance. So self-inductance means when we change the current in the coil, there will be an induced EMF in the coil, in the same coil. But mutual induction is quite similar except that it's involved two different coils. So mutual inductance is the process of producing induced EMF in one coil due to the change of current in another coil. Okay, for example, we have coil 1 and coil 2, and coil 1 has a power supply, its own current flowing through it. And then so due to the current, we have a magnetic field in coil 1. So if we change the current in coil 1, so the magnetic field passing through coil 2 will also change. So the change in magnetic field will cause a change in magnetic flux through coil 2. So the change in magnetic flux in coil 2 will induce EMF in coil 2. Okay, so EMF will be induced in coil 2. So the induced EMF is proportional to the rate of change of current. So the induced EMF from coil 1 is equals to negative M, where M is called the mutual inductance. It's a constant of proportionality, times with rate of change of current from coil 2. Okay, this is because when we change current in coil 2, induced EMF will be in coil 1. So the same thing happen if we induce current in coil 2 by changing the current from coil 1. So the mutual inductance, if we rearrange the equation, we get mutual induction. Mutual inductance is equals to the induced EMF divided by the rate of change of current. Mutual inductance can be calculated using the equation the flux linkage divided by current. So if the flux linkage happen in coil 1, so the current that is causing the flux linkage is from coil 2. So therefore, the equation is flux linkage coil 1 divided by current from coil 2. And it's also same vice versa. So if the flux linkage in coil 2 is divided by current in coil 1. So the mutual inductance of coil 1 with respect to the current in coil 2 is equals to the mutual inductance of coil 2 with respect to the current in coil 1. And the SI unit for mutual inductance is the same as self-inductance, which is Henry. That's capital H. Now let's look at the mutual inductance between two causal solenoid or a causal coil and a solenoid. So the equation is given as mu naught N1 times N2. Mu naught is the permeability of free space. N1 is the number of turns for coil 1. N2 is the number of turns for the coil 2. So it depends, either coil 1 is the solenoid or both are solenoid, or one is a coil and another one is solenoid. and times with A, which is the cross-sectional area, and divided by length of the solenoid. Let's see an example question. We've got a solenoid and a coil. So if the number of turns of the solenoid is 500 turns and the number of turns for the coil is 10 and the radius of the coil is the radius of the solenoid is 3.1 cm and the length of the solenoid is 75 cm. And the current in the solenoid is changing at the rate of 200 ampere per second. What is the EMF induced in the coil, in the surrounding coil? So first we have to find the mutual inductance between these two coils. So we can use the equation mu naught number of turn of solenoid times number of turn of coil times the area divided by length. Then we substitute mu naught times number of coil 500, number of turns of solenoid is 500, number of turns of coil is 10 times the area pi r squared, where the radius is 3.1 cm squared divided by the length 75 cm. So we get the mutual inductance is 2.53 times 10 power negative 5 Henry. And then we can calculate the induced EMF in the coil is equals to negative m di per dt, where I is the current from the solenoid. So the mutual inductance we have calculated 2.53 times 10 power negative 5 times with the rate of change of current is 200. So we get the final answer negative 5.06 times 10 power negative 3 volt. So that's the induced EMF in the coil. Okay, so we have come to the end of this video. Thank you for watching.